Now that we know the definition of graduation, which is majorly to smoothen out the crude mortality rates using some processes. One with an objective, one to establish a smooth flow across the ages, which can bring in the explainability of the mortality rates across different ages, but at the same time get more into the adherence to the observed values. So I am using the crude rates which I have observed, doing some kind of small tweakings to that observed rates, so that along with the adherence to the observed, I also see that the numbers are smoothly flowing across ages, so that the explainability and the premium computation can very well be handled. It cannot happen that in case of life insurance policies, the premium charged for a 20-year person is greater than the premium that is being charged for a 21-year person, and may immediately again drop for a 22-year. The explainability for the same will be much difficult. So what we typically see is a gradual change across the ages. So that is where we are using the smoothening mechanisms or the graduation kind of tools and techniques to bring out that kind of smoothening across the crude mortality rates, while at the same time ensuring the adherence to the data. That is one of the main objectives of using the graduation in our processes, majorly arriving at a compromise. Graduation, if I have to define it in a sentence, it is primarily a compromise between the adherence to the data and smoothness across the ages. So the best method is the one that handles both these things or balances both these things more effectively. And in this context is where we are trying to identify the three most commonly used techniques or tools. Three most commonly used tools to perform graduation. The first is with respect to the usage of a parametric formula. Means we try to use a formula, and using that formula we try to smoothen across the ages, right? So we are using a parametric formula kind of a method, or we are referring to a standard table, a standard mortality table, or a national statistics table which might have already been published. I am referring to that particular table, or finally I can look at even a quick graphical kind of an approach to do the graduation. And this is where now we start looking at the each of these approaches, the relative merits and demerits associated with each of the approaches, and how they can really fit in terms of balancing both adherence to the data as well as smoothness associated with it. So starting off with the typical parametric formula approach, when I'm going with the typical parametric formula approach, which means I'm choosing the most important thing for me in this process is I'm choosing one formula. So I choose a formula. It could be for the hazard rates. I could choose it as if it follows, let's say a Weibull distribution, or the formula, the hazard rate may follow a Gompertz or a Maycam. We have discussed these things earlier. The different mechanisms I can use for my hazard rates. I can even use a Gompertz Maycam family of R degrees and S degrees kind of a scenario. And when once I have used a formula, I can get into the estimation of the parameters used. I can use a mathematical or statistical technique so to estimate the parameters. Either I can use the least squares or error minimization kind of a mechanism, or likelihood maximization kind of a mechanism. I'm using different kinds of mechanisms finally to estimate the parameters using the observed values. Right, I'm taking one class of formula, and I'm trying to fit the data to that particular formula by using appropriate parameters, and based on that, either going ahead with minimizing the error least squares regression kind of a mechanism, or maximum likelihood kind of a mechanism. I'm using either of them to finally estimate the parameters, and once the parameters are estimated, then the formula is in place. Once I know the parameters, we see that the formula is in place, and now use that formula to compute the graduated rates. So I use that formula to compute the graduated rates, and so this is obviously smooth because it goes with a formula across the ages. Probably in some cases it may so happen that mortality rate increases with age. That kind of a formula can directly come out. So smoothing is not an issue here. So that's where I will test this particular data for adherence to the actuals. I can use some kind of chi-square test or some other kind of mechanisms to test the adherence to the data, and primarily in a real world behavior. So I just don't need completely smoothened out data. I also need that whatever the model that I have built, whatever the parametric formula that I have built, it works in the real world in the same way as we expect. So what generally happens is we try out this particular mechanism with almost every formula, and probably every sub formula that is linked with this formula. This is a very broad class of formula. Within this broad class, by changing the R and S, we can create n number of formulas with so many different parameters. We'll try out the model with almost all these parameters, all these possibilities, all these family of curves, and whichever the one that gives me the best fitment, either using a chi-square test, whichever is the one which minimizes my overall error, whichever is the one which is a best fitment tool, which is a best fitment tool, that is something that works quite comfortably for us in this using this kind of various families of curves. So in general, we can start off with a formula for the hazard rates, whichever we have discussed earlier. The Gompertz formula typically believes in the hazard rate following something like BC power x kind of a mechanism, where B and C are parameters. Or probably when I am going with Maycam formula, it goes as A plus BC power x. A is another parameter, generally representing something like an accidental death irrespective of the age. Or when I am using Weibull kind of a distribution, we said mu, the hazard rate follows alpha beta t power beta minus 1. Or when I am using a general formula for Gompertz Maycam family, we are seeing that mu which is the hazard rate, is going with a polynomial of r degree plus e to the power of polynomial of some s degree. So this is a general form of Gompertz-Makeham family of distribution, but whatever is the hazard rate I am using, all these are the different possible hazard rates I could use, right? There's no or probably I can go with any other particular formula also. But once I have used this hazard rate, one of the hazard rates, let's say I am using any one of the hazard rate, then I'm going, let's say I'm assuming the mortality rates based on a Poisson model. Let's say I have used any one of the hazard rates, and using this hazard rates I wanted to test the Poisson model for the expected number of deaths. So we know that in a Poisson model, the probability of death, the probability of observing dx number of deaths at and if let's say my expected central exposed to risk, which is the observed time with respect to risk, is let's say ex, the central exposed to risk is ex, then all we are seeing is we know that in case of a Poisson model, the probability of number of deaths being equal to dx is nothing but whatever is the hazard rate mu x plus half into ex central exposed to risk. That is what is the mean. Mean is mu x plus 2 x plus half into central exposed to risk in case of Poisson distribution. Even the variance or the standard, even the variance goes out to be the same. So that's where lambda power number of deaths observed e power minus lambda, lambda is nothing but mu x plus half into central exposed to risk, e power minus lambda, lambda power x by x factorial, so dx factorial. So when I use this and probably any of the mu related formula, especially to if I have to look at the likelihood function for the expected number for the number of deaths, for observing d deaths in an exposed to risk of ex, and I'm using a Poisson model for the same, and within the mu x I can go with the appropriate parameter kind of a formula. So this will tell me the probability of finding dx number of deaths using the fitted formula. Now in reality I would be having some other number of actual deaths. So I can test out the fitment to that particular the accuracy of the fitted value to that particular data using the appropriate assumptions. Now few things, whatever is the formula I am trying to fit, a few things which need to be kept in mind, some of the rules or some of the important checks that need to be done to see on a broader level if the graduated rates using any of the parameter formula are more or less adhering to the data or not. Though I can use a statistical test like a chi-square test to go ahead with it, I could also look at in general the mortality rate, the hazard rate for males. Is it greater than the mortality rate for females? In general, we find that the mortality rate for males is slightly higher than that of the females. And similarly, the mortality rate for a person who has taken life insurance policies should be greater than the mortality rate for a person who has not, or probably the overall population, because a person who really senses that there is a risk of death occurring for that person is someone who is more interested to show, is more possible to show a higher interest in terms of taking an insurance policy compared to the one who really believes that there is nothing that is going to happen to him in the next 5 years. So the high, generally from the data also we observe that a person with who has taken insurance policies will have the mortality rate slightly higher than the persons who have not taken the insurance policies. And similarly, or the mortality, probably that's the reverse, the mortality rate of a person who has taken the life insurance policy will be lesser than the person who has taken, who has not taken, because the person who has taken it, he has been examined thoroughly by the life insurance company. The medical tests have been performed on that particular person, and only after that an insurance policy has been issued. But for a person who has for whom the mortality risk is higher, probably he might have been denied the life insurance policy as well. So what you see is the mortality rate in case of people who have taken the life insurance policy will be lesser than the mortality rate of the population in general. And similarly, the other observation to look at is the mortality rate for people who have taken the policy recently will always be lesser than the mortality rate of the people who have taken the policy long time back. Again, the same logic, who have taken the policy recently, they have been examined by the insurance policy, they have been conducted medical tests very recently, and they might not have developed any kind of major complications within that recent period, compared to a person's whose medical tests have performed long time back, and over the period they might have developed some kind of complications resulting into higher mortality rate. So these are some of the common kind of quick checks that can be done to ensure, before getting into really a statistical kind of mechanisms of testing, whether my graduated rates are adhering to the actuals. So typically on a financial check, these are a very quick general checks, but on a financial checks, all these are very much important, because looking at these numbers is more and more important, because if I see from a life insurance policy perspective, the payment happens, the claim payment happens on the death of the individual. So if the mortality rate is underestimated, means the predictions are lesser than the actuals. So what could very well happen is the premiums that are charged will be much lesser. And if the premiums charged are much lesser, the collected premiums may not be sufficient for the entire claim payment. So probably it could result in losses for the insurance company. But on the other side, if the mortality rates are overestimated, means the more deaths than what are happening in reality, we could see that the premiums are charged very high, means it could very well be possible that they are uncompetitive. A competitor might price much better and take up the overall business. So the proper understanding of the graduated rates and the calculations are more and more essential to make sure that the mortality rates are neither too low nor too high, because both of them are a complication for the insurance company. The same is the case that goes with annuities, because the payment happens as long as the person is alive. The regular payments are going to happen as long as the person is alive. Now, what is happening there? If the mortality rates are underestimated, then if the mortality rates are underestimated, saying less number of deaths compared to the expected, the chance of death is lesser compared to expected, then probably the premiums that are charged are going to be much higher, because the pension payments happen only when the as long as the party is surviving. So if the overestimation of the mortality is there, then there will be inadequate premiums. But under the underestimation kind of a mechanism, again there would be in case the mortality rates are underestimated, again there could be an uncompetitiveness in the way the business is performed, right? So, and we are also seeing that the mortality rates, because of the improvement in the health conditions and research in the medical aspect, we see that the mortality rates have been continuously on a fall over a period. So again, when we are deciding the rates as of today, we have to even take into consideration the future possibilities and the future advancements that could happen in the medical science world, which could result in reduction of the mortalities in the future period, thus resulting in a change thus resulting in a change in the mortality rates, which could be taken into consideration for the pricing of the annuities, because the lesser the mortality rates are, the longer is the longevity of the person, and as long as the person is alive, the annuity payment needs to be made. So all these considerations need to be taken up as a part of our parametric formula to typically try to graduate the rates, providing more smoothing as well as adherence to the data. So when we are using the graduation using a parametric formula, appropriate choice of the hazard rate and taking into consideration all these aspects for doing a better fitment of the formula are some of the important considerations that need to be kept in mind, right? So with that as the base, let me slightly move towards the other mechanism of performing the graduation of the crude rate, that is with reference to a standard table. Right here in the graduation using a parametric formula, I'm choosing various formulas and seeing by using either maximum likelihood estimation approach or the error minimization regression kind of an approach, trying to see which of these broad class of formulas is a better fitment that reflects the actual rates along with the smoothing between them. Now the other mechanism that we are looking at is how do I graduate these crude mortality rates using a standard table. Alright. So when we refer to a standard table, generally what is that we call as a standard table? Any published life tables which have some kind of authenticity associated with them or reliability associated with them, and which are generally prepared based on a sizable amount of data either collected from insurance companies or typically collected from national statistics. So I can look at them as the national life tables, which are generally published based on the census data, where the entire population is taken into account, or they could be the tables which are prepared based on the insurance company's data on how many deaths have occurred during a particular period, having a sizable number of values based on the insurance policies kind of a data or information supplied by the insurers, or there could be a completely census based that are published at a national level. But whenever we are using the word standard table, it includes a sizable amount of data and a well-defined class of lives. All lives well clearly defined, but may not be homogeneous. I mean, different individuals have different risk characteristics, but at the same time, what we mean by this is the definition of the class of lives is very clear. Because otherwise, if the classes are completely different, probably gender wise, smoking status wise, if the definition is not clear, then probably there could be an overestimation in some of the cases and underestimation of the experience in some of the cases. So overall, the overall experiences may not be in relationship with the reality, and that is where things will fail. So the standard tables are prepared by taking into consideration broadly homogeneous I'm not saying perfectly homogeneous, broadly homogeneous lives, probably all males, smokers males, smoker female, non-smoker male. So standard tables might be prepared for each such kind of a class, with the prime intention being whatever the rates that are published, they are a decent representation for that particular homogeneous class. So for our particular crude rates, for the crude rates whatever we have collected, we wanted to do some kind of a graduation for this particular line of business. I wanted to do a graduation by using let's say the standard table. Now the first step for me is identify which table is more appropriate to me. Is it the national table? Right, identify the correct table which is more appropriate to my modeling requirement. Should I go with the national kind of a table, or should I go with the tables that are published based on the data of the insurance companies? What is the typical purpose I am going with? So identification of the current table, and after that, once a table is identified, find a simple link with your data, come out just like another formula, parametric formula kind of a mechanism itself, but here I'm trying to find a simple link, either linking out the discrete mortality rates or instantaneous mortality rates, either of them. So I can come out with a simple function, probably talking about the parametric rates, which are generally represented with a circle over the top. The parametric mortality rate is following a linear kind of a distribution with a standard mortality rate. Or probably I could have gone with, it follows a plus bx times the standard table's mortality rate. So we are trying to define some such kind of a formula linking the graduated rates and the actual rates that are there as a part of the standard table. So there is some kind of a link building exercise using different using a few parameters, in this case a and b kind of a parameters, and and probably I can try to identify this kind of a formula by doing some kind of a graph plotting also. Probably a graph plot between q circle x or qsx. They can very well be plotted to see what is the kind of a relationship that is existing between the graduated rates, which we have actually the observed rates, and so probably here if I am calling them more initially starting off with the observed rates, I'll try to plot a graph between the observed rates and the standard table rates. Based on this, I'll get a broader overview of overall shape that is existing between the two. Either I could do this or I could do it with the mu, whatever it is. I'll do the plotting for that, and based on that I'll choose an appropriate equation which would try to link the graduated rate, which would try to come out with a formula for the graduated rate by going with a least squares error estimation model by taking the standard table rates and trying to fit the parameters A and B. So the what is generally suggested is it is better to rely more on simple relationships like this itself. If I am trying to build a complex kind of a relationship, then I could see that my data more or less need not follow in any way similar to the standard table. My data may not be following the trend or a process with respect to that standard table, so there is no point in using the standard table as a base to do the graduation. So only simple relationships need to be experimented, but if no simple relationship like this is fitting well to the standard table, then probably the process itself need to be rethought. Means I don't need to consider the fitment to a standard table, probably a parametric formula or even a graphical method could be more and more appropriate. Right? Generally, what we observe is the data wise, whatever the data I am trying to use for the fitting purpose. In the middle ages, I find sufficient amount of data, so model fitting may not be an issue. But something at a very early ages or something at very extremely high kind of ages, getting the sizable data would always be a problem. So coming out with a better fitment, especially at too young and too old kind of ages are always difficult. But whatever may be the case, now the major intention is to identify these formula, the parameters based on this formula A and B. Again, here also I can go ahead using the maximum likelihood kind of estimation approach, just like the way we have worked out in case of parametric formula mechanism. Here also I could go with a maximum likelihood approach or the least squares error estimation approach, which is just like your regression kind of a mechanism. I could very well choose and finally try arriving at the parameters A and B. And based on once I have arrived at the parameters A and B, obviously my graduated rates are going to come up at every age. And once the graduated rates are in place, as I have been talking of earlier also, they are obviously smoother because they are following a particular formula. So the intention again, once they are graduated, my intention is always to check for the goodness of fit for that particular data. So we could use any of the tests. You could go with a chi-square test to check out for the goodness of it, to check out whether there is overgraduation or undergraduation. I can go for the science test, or probably I can look out for grouping of science tests, the various kinds of statistical tests which we have looked at earlier. They all can be very comfortably applied to test which appropriate formula is a better fitment to our model, right? So that is how we go ahead in terms of doing the graduation using with reference to a standard table. Now we will move further in terms of the third method of graduation, wherein we are following a graphical method, wherein we are discussing about a graphical method of graduation. That is what we will look at now. Right, again, the more we understand the various mechanisms going ahead with this graduation, the more comfort level comes in trying to identify the best fitted model to come out with the mortality rates at different age groups, right? Now, in the graphical method, my major intention is very simple: plot. I take the plotting process, I plot the crude rates, I plot the crude rates, plot the crude rate estimates,